Images are produced from inside a large cylinder similar to a CAT scanner. Inside the cylinder is a magnet capable of producing a powerful electromagnetic field. Since the atoms that make up human beings are electrical in nature, they are disrupted when the magnet is activated. Radio waves are then pulsated through the body. They gather information about the atoms as they return to their normal alignment once the magnet is deactivated.
And then the signal that comes back from that pulsation is constructed into an image of your organs or your brain or your ventricles or your knee or whatever it is that we're looking at. It's as simple as that. There is no X-ray, you have no radiation from it, it's harmless as far as anybody knows.
While CAT scans provide excellent images of bone and soft tissue, MRIs can see inside the bones. They produce images of blood vessels, cartilage, bone marrow, and ligaments, and are especially useful for detecting brain tumors. In 1993, it became the primary tool for a monumental effort to map the brain.
Brain mapping is defined in its title. It is the opportunity and the ways that we can map the human brain in health and disease, define its anatomy, and then understand its functions and how it works.
The University of California at Los Angeles is the lead center of the International Consortium for Brain Mapping. By studying thousands of MRIs of human brains, the consortium is gathering data that can have profound effects on medicine. For example, they can witness the brain's response to various medications, or actually see the early stages of various diseases.
We can look at the change in blood flow as a reflection of areas in the brain that are changing their activity, either up, more activity, or down. And that's what those techniques tell us. They tell us where in the brain something is changing when the person's doing a particular task. One of the really exciting parts about functional imaging of the brain is that you can have a way of understanding where in the brain things are happening and relate to certain behaviors. We can study learning directly. We can say, okay, how does the brain learn this? And when is it most efficient at learning that? Age 3, age 50, age 70? And we can pass on to the educators the real answers of how and when the brain learns something. That may have very important implications. For obvious ones are how we educate our children.
While MRI scans help us understand the brain through structural imaging, another computer-dependent imaging device can monitor metabolism in cells, spotting degenerative diseases such as Alzheimer's. Dr. Michelle Tur-Pagosian headed a program at Washington University in St. Louis that resulted in the first PET scanner in 1975. PET, short for positron emission topography, creates images by tracing small amounts of radioactive materials that are injected into the bloodstream. Inside a PET scanner are large rings of more than 20,000 detectors that work in concert to image the path of the radioactive substance.
It has penetrating radiation, like the X-rays are inside of you. And so the X-rays come out and they hit the detectors, and those detectors record every single event. And then those events don't really look like a picture. You have to actually reconstruct it. And then what you'd actually make is a 3D picture of your insides.
Once again, to the untrained eye, the image produced by a PET scan does not look as clear as a CAT scan or even an X-ray. Instead, doctors interpret the image by how the radioactive tracer interacts with the body's chemistry. In doing so, they can actually see evidence of disease not visible through other imaging devices.
Everybody has said for years that you cannot diagnose Alzheimer's disease except by autopsy, where you cut out the brain and look at it. Well, since 1980, we've been able to see Alzheimer's disease very easily with the PET scan. It just turns out that big parts of the brain are essentially missing because that's what's being destroyed.
With such powerful imaging devices at their disposal, doctors and scientists were seeing more of the human body than ever before. And with the advent of the internet, so would the rest of the world. These amazing images are one of a kind. They are from the first three-dimensional computer model of a whole human being, a virtual cadaver. It's called the Visible Human Project, and its purpose is to provide anatomy students with a model that can be sliced in thousands of different angles and put back together again.
That's important for teaching whole body anatomy, as you teach a medical student to, they all interact with whole bodies. You want them to see what a body looks like and be able to visualize what things deep to the surface of the body are. They only see patients generally from the skin or even from the clothing, and to visualize where the upper left quadrant of your liver is relative to your abdomen, how deep it is, where it is anterior to posterior. It is important to get that three-dimensional view across to people, and being able to reconstruct this in the computer was the driving force here.
The Visible Human is a marriage of CAT scan, MRI, and digital photography. It was constructed at the University of Colorado and is freely available on the internet to anyone wishing to digitally dissect it. One of the more bizarre challenges to creating the Visible Human was finding its real-life model. A young male cadaver in as good a physical condition as possible. The ideal choice would be a drug overdose victim, somebody with no visible signs of trauma and with organs not suitable for donation. 39-year-old Paul Jernigan of Waco, Texas, fit the bill. When he killed a 75-year-old man in an attempt to steal a microwave oven, Jernigan was sentenced to die by lethal injection. The execution was carried out on August 5th, 1993. Having willed his body to science, Jernigan was airshipped to Colorado soon after his death. CAT scans and MRI scans were immediately taken by Spitzer's team. Next, the body was encased in a special gel and frozen beneath cakes of dry ice. Then came the hard part. The rock-solid frozen cadaver would have to be cut into quarters so that it could fit into a custom-made slicing device called a chiromacrotome.
Then each quarter is then encased or made into a large ice cube. We pour it into a mold, gelatin, which surrounds that part of the body, and make a 20-inch tall by less than 22-inch wide by less than 14-inch deep ice cube, if you will, that contains this specimen.
The cadaverous cube is then placed into the chiromacrotome. 1 millimeter at a time is sliced off the block.
Here we've frozen everything solid as a rock. The skull and the brain are both the same kind of hardness. So when we cut, they react the same way. And you don't have different kinds of distortion of the brain and the skull.
After each slice is removed, the cube is sprayed with alcohol to melt the frost. Next, a digital photograph is taken. More than 1,800 slices and photos are made in all. The images are then stacked and programmed into an imaging computer, where virtual slices in any direction can be made by users. The Visible Human can also be explored entirely through MRI or CAT scan images. The project's directors see even greater possibilities for future virtual humans.
Right now, it's a good simulator for a cadaver. It acts like a cadaver. And it will keep moving until it acts more like a live human. A man that has a beating heart, a man that has blood flowing through his body. We're not there today, and it's not happening today, but that will happen.
Such a future may be close at hand, thanks to rapid advances in digital technology and an unquenchable thirst to witness the magnificent inner workings of the human body. Wilhelm Röntgen could never have ever envisioned that his dogged exploration of a mysterious glow would lay a foundation for later scientists who would invent a wide array of powerful imaging techniques. Their genius will surely inspire the future of medical imaging, one that holds promise of seeing deeper, further, and with exquisite clarity.
All right, guys, go ahead and let's take a break. We'll come back in about 10